Hey guys, this is Dilip, Shreya,
Charan,
Kirtana,
and we're here to explain the unexplainable. Have you ever thrown your phone into the air?
But wait, why did it flip mid-air? Okay, let's go slower this time and see what actually happens. This phone has three principal moments of inertia about these three axes. This is axis 1, and the phone has the highest moment of inertia about this axis. This is axis 3, about which the phone has least moment of inertia. And this is axis 2, which we are going to call the intermediate axis. We rotate the phone about axis 1 and 3 and we observe a stable rotation. But the rotation about the intermediate axis is always unstable. Why?
This is called the Dzhanibekov effect. It is explained by the intermediate axis theorem, sometimes also called the tennis racket theorem.
To explain the tennis racket theorem, we use Euler's equations for rigid body dynamics. Basically, Euler has given us equations to observe the rotation of a rigid body from a rotating reference frame. The coordinate axes of this frame are fixed to the rotating body and parallel to its principal axis. The general form of the equation is this, where m is the applied torque, I is the inertia matrix, omega is the angular velocity about the principal axis, and omega dot is the time derivative of omega.
And applying this to the three dimensions of the coordinate system, we get where mk are the components of the applied torques, ik are the principal moments of inertia, and omega k are the components of the angular velocity about the principal axis.
Here, we assume that I1, I2, I3 denote the object's principal moments of inertia, and we assume I1 is greater than I2, which is greater than I3. The angular velocities around the object's three principal axes are omega 1, omega 2, and omega 3, and the time derivatives are denoted by omega 1 dot, omega 2 dot, and omega 3 dot. To explain the stable rotation about first axis, we take the initial angular velocities along axis 2 and 3 to be extremely small. Observing equation 1, we see that d omega 1 by dt is extremely small, so much so that the time dependence of omega 1 can be neglected. Now, differentiating equation 2 and substituting omega 3 dot from equation 3, we get we see that the double derivatives of omega 2 and similarly omega 3 are negative quantities. From the properties of the second derivative, we see that if f double dash of x is less than 0, then f has a local maximum at x. This means that omega 2 and omega 3 are at a local maximum currently and will only tend to decrease. So rotation about axis 2 and 3 does not happen and omega 1 dominates the rotation. Similarly, we can show that rotation about axis 3 is also stable.
Now let's look at axis 2. This time omega 2 dot is very small. Therefore, the time dependence of omega 2 may be neglected. Now, differentiating equation 1 and substituting omega 3 dot from equation 3, we get the second derivative of omega 1 and similarly omega 3 are positive quantities, and this means that they currently have a local minimum. Hence, they can only tend to grow. And because of this tendency, even a small disturbance along axis 1 and axis 3 will cause the object to flip, and this makes the rotation unstable. Here's a quick comparison.
So the next time you throw your phone in the air, be sure to observe its intense rigid body dynamics.
Make sure you catch it after you throw it.
You don't have to, okay.
Don't throw a Samsung, it'll explode.
Hey, maybe I should try this.
Don't do it!
What do you think?